Hello everyone. In this video we will discuss deformation, retracts and homotopy type. So this is basically one way of finding the fundamental group of any space. We have already done that if we want to obtain any information about fundamental group of a space, then that can be done through study of covering spaces of that space. But this is another way uh, to find the fundamental group. This deformation, retracts and homotopy type basically they gives a method for reducing the problem of computing the fundamental group of a space to computing the fundamental group of some other space, and that other space is much familiar to us. So we start with the lemma. Firstly, if we have two maps H and K, which are from x naught to y naught, and if these two are continuous maps uh, which are homotopic to each other, and if the image of the base point x naught that remains fixed throughout the homotopy, then the homomorphism induced by H and K, which means H star and K star, they are equal. So if H and K are continuous maps from x naught to y naught, it means they are continuous maps from x to y and they map x naught to point y naught. And if they are homotopic, and image of base point x naught that remains fixed at point y naught throughout the homotopy, then the induced homomorphisms H star and K star, they are equal. So let us prove this. The proof is very obvious. Because if H and K are homotopic, and let us assume that H is a homotopy between H and K, so H will be basically a mapping from X cross I to Y. So let this be homotopy between H and K. So basically we are assuming that H of X naught T, sorry, X naught 0, not X naught, H of X0, this is Hx, and H of X1, this is Kx for each X in X. And second thing we have given that the image of the point x naught remains fixed at y naught throughout the homotopy. So it means if we take point x naught in space X and take any t in I, that remains fixed at y naught. So this is for every t in I. So these all things are given to us. Now if we want to prove H star and K star are equal, that means we want to prove that if F is a loop, if F is any loop in space X based at X, because we know domain of H star and K star, that is fundamental group of the space X based at X naught. So if F is a loop in X based at X naught, then we have to prove actually H star of homotopy class of F is equal to K star of homotopy class of F. That means we want to prove that homotopy class of F, H circle F, that is equal to homotopy class of K circle F, which means we want to prove H circle F and K circle F, they are path homotopic to each other. Now we can see that if we define the mapping F from I cross I to Y by F is H circle F cross identity mapping, because we need a mapping from I cross I to Y to prove H circle F and K circle F, they are homotopic. So we have a mapping capital H from X cross I to Y. Then we define this composition. This is basically the composition I cross I to X cross I, which is given by F cross identity mapping. This F is from I to X and identity I to I. And then X cross I to Y, we have this capital H mapping. So we take the composition of these two mappings as our capital F mapping, and then we will prove this capital F is a homotopy between H circle F and K circle F. Now this is a continuous map because H and F both are continuous maps. And secondly, F of S0, this is H of F cross identity at S0, and this is H of Fs and 0, H of Fs and 0, this is basically H of Fs. And similarly we can prove Fs1, this is now H of x1, that is K so K of S. And secondly F0t, this is H of F cross identity at 0t. So this is H of F0. So F0 is x0 because F is a loop based at x0. And Hx0 t is y0. Similarly, F1t, F1 is again x0. This is y0. So we have proved here that H circle F is homotopic to K circle F. So it's path homotopic to K circle F. So basically the homomorphism induced by H and K are equal. So now in the next theorem, we will prove that we have already proved that the mapping induced by inclusion map J from S1 to R2 minus 0, this is injective. We have proved that if this is inclusion map, then J star is injective. So now using the above lemma, we will prove that if we define inclusion map J from Sn to Rn plus 1 minus 0, then the mapping J star, which is induced homomorphism, that is not only injective but surjective also. So it means it is an isomorphism. So let us prove this. The inclusion map J This induces an isomorphism of fundamental groups. Let us take X to be the space Rn plus 1 minus 0 for just simplicity. And we take a point B naught of the n sphere Sn, which is given by 1, 0, 0, 0. Let this be the point of Sn. And we define R from X to Sn by Rx as X upon norm X. Now, because we are taking this small x in the space X, and space X is basically Rn plus 1 minus 0. So this X is non-zero point. So we can divide it by norm of X. And when we divide X by norm of X, it will be a point of Sn because its norm is 1. Now, this R circle J, this will be identity map. If we define R like this, then R circle J will be identity map of X. Identity map of Sn, sorry. So if this is identity map, then R star circle J star, that is also identity map. And it means this is identity homomorphism. Of the fundamental group of space Sn with respect to, let us say, point B naught. Now we take the composition map J circle R. Now J circle R is a mapping which is not identity map of X. Basically, this is a mapping of X to X, and it is given by this. X goes to Sn, firstly under the mapping R, and then under mapping J, it again goes to X. So this is not identity map of X, but it is homotopic to identity map. Let us see how. We define mapping capital H from X cross I to X by H of X t. This is 1 minus t into X plus tx upon norm of X. So this map will work as a homotopy between J circle R and the identity map of X. Now this mapping HXT, this is non-zero. This is never zero because we want to define mapping from X cross I to X, and X is basically Rn plus 1 minus 0. So we have to prove that this mapping HXT, this is never zero. So now this number 1 minus t into X plus t x upon norm X, this is a point lying on the line joining 1. This is the point lying on the line joining X and X upon norm X. So, and secondly, for any t lying from 0 to 1, the number 1 minus t plus t upon norm X, that is a number lying between 1 and 1 upon norm X. So since this number 1 minus t plus t upon norm X, this is a number between 1 and 1 upon norm X. And we know norm of B naught, because we have assumed the point B naught is 1, 0, 0, 0. So norm of B naught is 1, and H of B naught t, that is equal to 1 minus t into B naught plus t into b naught divided by norm of b naught, and since norm of b naught is 1, so this number is simply equal to b naught. So we can see here this H, capital H, is a homotopy between J circle R and identity map, and this is a homotopy under which the point B naught remains fixed throughout the homotopy. So we can apply the previous lemma, and by previous lemma, this J circle R star, this is identity homomorphism. Because in the previous lemma we have proved if H and K are homotopic, and if point X naught remains fixed throughout the homotopy, then the mappings H star and K star are equal. So here we are saying J circle R is homotopic to identity map, and point P naught remains fixed throughout the homotopy. So J circle R star is equal to identity star, but identity star is identity homomorphism. So we can say this is identity homomorphism. So it means J star circle R star, this is identity homomorphism. So we have proved here that J star circle R star is identity, as well as R star circle J star is identity. It means J star, that is bijective map. So it is isomorphism basically, which completes the proof. In this lemma, in this theorem, we have proved that J circle R, this is homotopic to identity mapping. And during the homotopy, the point B naught remains fixed. Basically, not only point B naught, but all the points of the sphere Sn, they are fixed during this homotopy, because if we take any point on the sphere Sn, then that point has norm is equal to 1, and for that point H, and for that point the image H of that point at and T, that will be the same point. So basically here we are proving that J circle R, which is actually a mapping from Rn plus 1 minus 0 to Rn plus 1 minus 0 itself. And this is basically a mapping which maps whole of the space Rn plus 1 minus 0 to Sn, because this mapping J is inclusion map. So this composition J circle R, this is a mapping which maps actually whole of space Rn plus 1 minus 0 to space Sn. Or we can say it collapses whole of the space Rn plus 1 minus 0 to Sn. And this is homotopic to identity map of the space Rn plus 1 minus 0. And these two mappings are homotopic. And during the homotopy, whole of the space Sn, that remains fixed. So this type of situation is called deformation retract. So let us firstly define deformation retract. In general, if we take a subspace A of X, then A will be called deformation retract of X. If firstly the identity map of X, this is homotopic to a map which carries whole of X into A and secondly, every point of A remains fixed during this homotopy. So what is deformation retract? Deformation retract, a subspace is called deformation retract if firstly we define identity map I from X to X, and secondly if we define some mapping, let us say F, which carries all of X into A, and if these two mappings are homotopic to each other, and during the homotopy every point of A remains fixed. So we can define the situation like this: if there is a continuous map capital H from X cross I to X, this is basically the homotopy map, such that first of all Hx0, because we are saying that these two mappings are homotopic to each other, so Hx0 is Ix, or we can say this is X, and Hx1 is equal to Fx, and F is the mapping which carries whole of X into A, so it means Hx1 belongs to A. So if these two conditions hold for every X in X, and third condition is that each point of A remains fixed during the homotopy. That means if we take any small a in A and take any t in I, that is equal to A itself for each A in A. So if we can prove that there is a continuous map from X cross I to X such that Hx0 is X, Hx1 belongs to A for every X in X, and Hat is equal to A for every A in A, then we say that A is the deformation retractor of X. And in this case, we will say H is a deformation retraction of X onto A. H is deformation retraction of X onto A. And if we have a deformation retract, then we can define a retraction. So let us see how. We define the map X from, define mapping R from X into A by Rx as H of X1, because we know H of X1 belongs to A if H is a deformation retraction. Now this mapping R is a mapping from X into A such that it is identity map on the space A. R of A, that is H of A1, and H of A1 is A, because of H of AT is equal to A for every A in A and for every T in I. So since this is a mapping from X into A such that R restricted to A is identity map, so this is a retraction. So R is a retraction of X onto A. And in this situation, this capital H, which is a homotopy between a mapping identity and the second mapping which takes whole of X into A. So basically this H will be a homotopy because we have defined Hx1 is equal to Rx. So the second map becomes R, and H will be a homotopy between identity map of X and the mapping J circle R, because R is a mapping from X to A and J is the inclusion map from A to X. So this composition is a mapping from X to X, which maps every element into A actually. So where this J is inclusion map. So basically we can say that a subspace A of space X is called deformation retract if we can find a mapping capital H from X cross I to X such that H of X0 is X and H of X1 is in A, and H of AT is equal to A for every A in A. And basically this H will be a homotopy between the identity mapping of X and the mapping J circle R, where J is inclusion map and R is the retraction map defined like this. Rx is equal to Hx1. So we have proved above that the mapping, the the homomorphism J star induced by the inclusion map from Sn to Rn plus 1 minus 0, that is actually isomorphism. So from that theorem we have the immediate generalization, and that is given by this theorem. Now in this theorem we will prove if A is a deformation retract of X, then the inclusion map J, let us take Ax naught to Xx naught. Here we are fixing the base point as x naught. So this induces an isomorphism of fundamental groups. So basically in this theorem we are proving if A is deformation retract, then the homomorphism induced by this inclusion map J, that is actually isomorphism. So because of the definition, this is quite obvious, because if A is a deformation retract, then we have this capital H mapping from x cross I to x, such that h of x0, this is x, and h of x1 belongs to A for every x in x, and h of at, this is A for every A in A and for every t in I. And we have to prove that J star is isomorphism. So because of this deformation retract, if we define mapping R from X to A by Rx is equal to Hx1, then we can easily see that J circle R and identity mapping, they are homotopic to each other, because this H will now work as an as a homotopy between identity mapping and J circle R. So it means J star circle R star, this is equal to identity homomorphism. And secondly, R circle J, this is equal to identity map, because J is inclusion map, so J maps A to A for every A in A, and R is given by Rx is equal to Hx1, so that is identity map, because H fixes all the points of A. So if this is identity, then R star circle J star, that is identity. So if both the compositions are identity, that means J star is isomorphism. So it means J star is isomorphism. So this proof is quite obvious. So now from this result, we can see that Sn is a deformation retract of, the first example of deformation retract is Sn. So this is a deformation retract of Rn plus 1 minus 0. So let us take one more example. Now let us take B to be z-axis in the space R3. And now we consider the space R cube minus B No, this space R cube minus B, this has a deformation retract equal to x, sorry, R2 minus 0 cross 0. So R2 minus cross 0, this is basically the punctured xy plane. R2 minus 0, R2 is xy plane minus 0, so it is the punctured plane at point 0, means it is the plane which does not contain its 0 element. Cross 0, so cross 0 means it is the plane where zx is equal to 0. So this is basically homeomorphic to R2 minus 0. So we can say that this is the punctured xy plane. So now in this example, we will prove that if we take x to be R3 minus b and a to be this R2 minus 0 cross 0, this is punctured xy plane, then this a is a deformation retract of this space x. And to prove this is a deformation retract, we have to define a mapping H from x cross I to x, which satisfies the condition of being deformation retract. So we define here, now here this x, this is a subspace of R3. So the points of this x are given by x, y, z, the triplets. And this t belongs to I. So we will define H. We define h of x, y, z, t by x, y, 1 minus t into z. Actually, we have to define this mapping h like this, that h of x, y, z 0, that is equal to x, y, z, and h of x, y, z 1, that belongs to a. So if we define the mapping like this, then it will be continuous, obviously. And we have to define it from x cross I to x. So we have to define this ordered pair of 4 elements to triplet. So we can define like this. So now let us check the conditions of deformation retract. So we put t is equal to 0, and this will be xyz. So h of xyz 0, this is xyz. That means it is identity at hx0. And the second condition, if we take t is equal to 1, then it will be xy0. And xy0, this belongs to a, because a is R2 minus 0 cross 0. And third thing is, if we take this point xyz in a, means if we take this xyz as the point of R2 minus 0 cross 0, means as the point of xy0, where xy belong to R2 minus 0, means both of these points x and y cannot be 0. And we take t here, then we get x, y. Now since z is 0 here, so it is also 0. So xy0 t is xy0. So this remains, it means all the points of the space A remains fixed during this mapping H. So all the conditions are proved of deformation retract. So we can say A is deformation retract of X. And this mapping H, which we defined here, that is a deformation retraction. So this is the mapping basically, which collapses each line parallel to z-axis into the point where this line meets the xy plane, because we are taking here t from 0 to 1, and we are taking here 1 minus t into 0, means that point where it intersects the xy plane. us take one more example of deformation retract. Now consider this doubly punctured plane R2 minus P minus Q, the plane which is punctured at two different points P and Q. So we can consider it as a figure 8. So this space basically, this has figure 8 as its deformation retraction. Deformation retract. So let us see how. Firstly, we have this type of space. Let us say this is point P, this is point Q, and this is our R2 minus P minus Q. So we can deform it in different stages. In the first stage, we will deform whole of this because we can continuously deform the space where these 2 points does not lie in that plane, because the plane is punctured at these 2 points only. So we deform, we take a circle which contains both of the points P and Q, and we deform the outside region of this circle to the circle. So this is the first stage of deformation. We deform whole of the space R2 into this open or into this closed ball which contains the point P and Q. Now in the second stage, we deform these 2 points to the circles. This point P, this is deformed into the circle. Similarly, Q is deformed into the circle. And in the next stage, we deform this to a circle like this. So this is point P, this is point Q. So we deform the points P into these circles. And then we deform whole of this area to this point lying on these boundaries. Similarly, the area below this, that will be deformed like this, and we will get only this type of space, this and this. So we get a figure infinity. So we can say that figure infinity is deformation retract of the space R2 minus P minus Q.